Welcome to Spring LIB.
Okay, in this problem we are asked to find the total electrostatic energy of an insulating sphere. We're given its radius, r naught, and its total charge, big Q. So to start off, we need to note that for a generalized charge distribution, a small amount of energy is simply the electric potential times a small amount of charge, and we're going to integrate this here. The next thing that we can do is we can relate the charge density to the total charge in the dimensions of the sphere. So if we assume that the charge is uniformly distributed over the volume, we can write the charge density as the total charge over the volume of the sphere, 4/3 pi r naught cubed. For an arbitrarily sized radius inside the sphere, we can also express the charge density as the little q, the charge inside that smaller sphere, 4/3 pi r cubed. And since these should be equal to each other, the charge density is uniform throughout, we can set these both equal to each other. So big Q, 4/3 pi r naught cubed is equal to little q, 4/3 pi r cubed. And we can find the total charge within a subsphere with respect to the total charge in the larger sphere, our current radius, and the radius of the entire sphere. So we're going to be using this relation throughout. It's also worth noting that the voltage of the surface of the sphere is simply that of a point charge, where little q is the charge contained within our sphere, r is the radius of our subsphere. We can plug in little q to express this in terms of other radii and main charge. So we have 1/4 pi epsilon naught, big Q, r squared over r naught cubed. Okay. So at this point, we're going to integrate thin shells of charge to find their energy. And these thin shells will have a charge of dq. We can express the charge contained within a shell, a very thin shell, to be the charge density, rho e. The area of the shell, pi r squared, times a small little change in dr to account for the thickness of the shell. Thus, the total electrostatic energy is an integral of energies contained within each of these subshells, v dq. And we integrate out to the total radius of the entire sphere. We can plug in our electric potential now. Big Q, r squared over r naught cubed, rho e. We can now change our differential to be so that our integral is in the radial direction. We can evaluate this integral, which is not too difficult. We end up with rho e q, or epsilon naught, rho naught cubed, integral of 0 to r naught, r to the 4th dr, easy integral in radius. We're left with 3q squared over 2 epsilon naught, over 20 rather, sorry, 20 epsilon naught, r naught. And that's it. This is the total electrostatic energy of the sphere.